There is a spot in the ocean where the planet's biggest climate trend seems to break down. Pretty much the whole world has warmed since the pre-industrial era, but not this spot. Scientists call it the cold blob or the North Atlantic warming hole. And the question is, what's causing it? Why has this spot escaped global warming? Well, the leading theory is that it's a bad thing, that it's a sign that we humans might be changing how the ocean moves.
Ocean currents in the Atlantic may be on course to collapsing.
What happens if those currents do collapse, and how likely is that? To understand what's causing the cold blob and how bad this could get, we're going to visit the sites of 7 key discoveries that unlocked the secrets of the ocean. It'll take us 12 Eiffel Towers down below the surface, and when we get back, you probably won't look at the ocean the same way again.
You hear that, commenters? We're using Eiffel Towers as a unit, not Empire State Building, even though we're American. So I hope you're happy.
Oui. We'll start our tour here, where humans first discovered salt-driven currents.
This is Turkey, right?
This is Turkey. This is the Bosphorus Strait, and water here flows from the Black Sea out to the Mediterranean. But a long time ago, local fishermen noticed that when they lower nets off the back of their boat in the direction of the current, sometimes their nets would surface in front of them. So in 1680, a young man visiting from Venice decided to investigate this. His name was Luigi Ferdinando Marsili, and all of the images of him online look like this, but he was really just 21 years old at the time.
Okay.
He put his boat in the middle of the strait and used a weighted rope to show that 10 to 20 meters down, there was a current flowing in the opposite direction of the surface. But why is it doing this? So Marsili collected some of the water from the surface of the strait and some of the water from below, and when he opened up holes between the two sides, the water started moving like it did in the strait. So one current on top, another one underneath, moving the other way. It turned out that the water from the deeper current was saltier. If you look at a salinity map, you can see the Mediterranean there.
Wow, it's dramatic. I mean,
Right.
and the Mediterranean is even extra salty.
While on the other side, we have fresh river water. It's less dense. So why exactly does this difference create a double flow?
Yeah, why does it create a double flow? I don't actually understand why that would be.
Salty water is just heavier. And
Okay.
when it can't keep pushing downwards, it starts to push sideways. So that difference in pressure creates the double flow that the fishermen observed.
Gotcha.
And this little waterway was kind of the perfect place for humans to discover that it's not just winds and tides that make water move, density does too. But this all gets more interesting when we look for it in an ocean that is 50 times deeper.
To the ocean.
We are jumping ahead 70 years, and this is where we have the first recorded deep sea temperature at this spot.
Temperature.
It was taken by a British slave trader on his way to West Africa. And at this point in history, there are huge numbers of ships going across the ocean, carrying enslaved people and the products of their labor. And the navigators have become familiar with the wind-driven surface currents that, speed up or slow down their ships. But they're still oblivious to what's going on down in the deep. Until, in 1750, this guy drops a bucket with a thermometer down 1,600 meters, pulls it up, and gets a surprising result. Ice-cold water under a hot tropical ocean. Now, it took a few decades before anybody actually understood the significance of this, but eventually some people proposed that the deep water was cold because it had moved there from the cold parts of the planet, from the poles. One of those people was Benjamin Thompson, also known as Count Rumford. This guy had a wild life. There's a whole book about it. But this Count Rumford had recently discovered convection currents by accident when he noticed dust particles circulating in a thermometer that was heated by sunlight. What is the best way to understand convection currents? Or, why temperature differences can circulate water?
Well, it seems like it goes back to density again. If it's expanding, that means it's less dense, and that it would rise.
Exactly.
Whereas heavier stuff would sink.
So Rumford reasoned that at the poles, cold water would descend to the bottom of the sea, flow towards the equator, and thereby produce a current at the surface in an opposite direction. So by the 19th century, a picture is forming. Cold water sinks at the poles, rises at the equator. It's elegant, it's symmetrical. But this was not quite right.
Ah, dang.
They understood that density differences could cause water to circulate, and they understood that salinity and temperature determine density. But you gotta go out and measure the ocean if you want to understand the currents behind the cold blob.
Okay, we're going down South America way, Argentina, it appears.
This was the starting point for a German expedition in 1925, where they zigzagged across the South Atlantic.
Very fun.
Actually, it was really slow and repetitive. Sail a little, stop, lower instruments into the deep, haul them back up, write down the data, continue along, stop, do it again. They did that for 2 years. This was a much more comprehensive survey of the Atlantic than what the British Challenger expedition had done 50 years earlier. And as the data came in from all these expeditions, the understanding of how water flowed between the poles became much more nuanced.
Okay, we've got to the left is north with Greenland and Iceland, and then we've got Europe and Africa kind of in the backdrop.
Right.
And then to the right, it's all the way south with Antarctica.
When you mix salt and temperature together, you get fingerprints of water masses, is what they call them. Water masses, like...
They have like a distinctive salinity and temperature. So you're like, oh, this is definitely Antarctic bottom water.
Exactly. They have a distinctive mix of those two things that decides how they layer and how they flow through the Atlantic. And a key thing to get here is that these arrows that we see were not currents that anybody directly witnessed. They're inferences that they're making by measuring temperature, salinity, and oxygen. It took another expedition to actually catch the deep current in motion, and they did it right here.
Off the coast of the good old US of A.
So it's the late 1950s, and there's a weird sound coming from this spot. It's a 10 kilohertz signal from an aluminum device designed by an oceanographer named John Swallow. And this aluminum tube was very carefully weighed so that it would sink to a specific depth where the density of water was known and stay at that depth. Then they just listened to it. And by doing that, they actually, for the first time, tracked the motion of a current way below the surface.
Okay, how do you go from sound to mapping a current?
So they would kind of triangulate its location with these two hydrophones.
Gotcha.
And they followed along, and they realized that it was moving pretty quickly. So at the surface where their boat was, the Gulf Stream is racing north. This is the big wind-driven current that runs along the Western Atlantic on the surface. But 2,000 meters down, they saw their floats moving quickly southward. And that confirmed that when water sinks in the North Atlantic, it doesn't just move south as a broad, even sheet. It's concentrated along the western edge of the ocean near North and South America, and that's because of the spin of the Earth. So, when you put together all of that research and much more, we get planet Earth's overturning circulation.
Wow, this is beautiful.
In red, we have the surface currents made of lighter water. They're very influenced by the winds. And the blues are deeper currents. And there are only a couple of places in the world where the surface waters become dense enough to overturn and become deep currents. That happens in the Southern Ocean near Antarctica. And more importantly for us, it happens in the North Atlantic. By sinking there, it helps keep the red surface waters moving north, shaping weather far and wide. We call this system the AMOC.
The really special thing about the AMOC is that it's a circulation that crosses the equator, goes from south to north across the Atlantic, right? And actually transports heat, changing the heat balance on the whole globe.
If we were to say head west from London, we would hit Newfoundland, you would get to Canada. And they have huge extremes in temperatures, don't they? From really, really cold winters to these real extreme summers. Where the UK and Europe is a bit more well-behaved in the weather, actually. It's a bit more temperate, and that's due to the ocean and the heat supply from this ocean circulation, this AMOC.
That brings us back to the mystery that we started with.
Back to the cold blob.
Back to the cold blob. If less heat is making it north, that would show up as a cold blob on the surface of the ocean south of Greenland. Right now, we are pushing on this system in two different ways at once, because we learned that both temperature and salinity can change the density of water.
We're certainly heating up the atmosphere, which is eventually getting absorbed a lot of that extra heat is getting absorbed by the ocean. So you got the temperature going up, but that's also melting a bunch of ice that's on land, and that is entering the ocean and making it less salty.
Exactly. And the reason that this gets extra attention is because of the possibility of what they call a nonlinear change or a tipping point, because the salinity part of the system has a feedback loop.
So what's the feedback loop with salt?
Well, the salt is concentrated around the subtropics, and the AMOC pushes that salt north.
Gotcha.
So as the salinity combines with the colder temperatures, it causes the water to be dense enough to sink. So in the Pacific Ocean, it gets just as cold, but there's no sinking because it's not as salty.
Basically, the more fresh water that gets dumped in the North Atlantic, the lighter the surface water gets, so it doesn't sink as easily. And that weakens the circulation, brings less salty water north, and that makes the water even fresher, and so on and so on.
Exactly. The circulation brings the salt, and the salt pushes the circulation.
That's why the AMOC, we're worried about it, because it's sort of like the AMOC's existence lets it exist.
Okay, that doesn't sound too good.
Yes. There's this real fear that this feedback loop will send the system past a tipping point where no matter what we do, the circulation becomes much weaker and stays weak for a long time. And we know that this is not just a theoretical possibility because it has happened before. And to show you what I mean, we have to visit the ghost of climates past.
All right, so we're heading up to Greenland, and I think that means ice cores.
Yep. But really quick, open your Slack because I want to show you a tool that I've been trying out.
Sure.
Okay, I'm writing this message without typing. I'm just using my voice, which is so much faster.
Whoa, instantaneous.
Pretty cool, right? So this is WhisperFlow, which is the sponsor of this video. It's installed on my laptop, so no matter what application I'm using, I just hold down a hotkey while I'm speaking and boom, done. And on my phone, I can just choose it as one of the keyboards. What makes it better than the built-in dictation tools is that it is so much smarter. Jump into this Google Doc. This is a list of 3 things to know about the Sverdrup.
What's Sverdrup? And how did it know how to spell Sverdrup?
It is the unit of measurement that they use for the strength of the AMOC. It means 1 million cubic meters per second. It was coined because oceanographers were tired of saying 1 million cubic meters per second. It was named after a pioneering Swedish oceanographer named Harald Sverdrup. He was Norwegian.
I see, so it corrected that from what you originally said to Norwegian.
Yeah, it's nice, right? If you want to give this a try, you can get 30 days free of WhisperFlow Pro by using the link in our description. And let's get back to the story. It's the 1960s, and something huge is happening 8 meters under the surface of the Greenland ice sheet. This is the site of Camp Century, which is an American base that was built into the ice. It had dorms for 200 people. It was all powered by a nuclear reactor. Officially, it was a research station and an engineering experiment. It came out in the 1990s that the US was hoping to station hundreds of nuclear bombs there. That did not work out, but they did do some science that changed how we look at the planet. So for 3 years, they drilled into the ice sheet and pulled out a core that held 100,000 years of snow. There's a paleoclimatologist named Willy Dansgaard, an exceptionally stylish Danish scientist.
He's got that pipe.
He had recently figured out that oxygen atoms in the ice could tell them something about the temperatures throughout history. And so this is the record from the Camp Century ice core, and this was a revelation.
The y-axis going up and down is the depth of the ice core / how far back in time we're going.
Yes.
And then
warmer to the right.
Warmer to the right, colder to the left. Gotcha.
And it revealed climate changes that were way faster than anyone expected. So not just these orbital cycles over tens of thousands of years, but wild swings over centuries and even decades. So scientists drilled more ice cores in the 80s and 90s and confirmed that indeed the wiggles were real.
It was not an accident of the ice flow. It was not a bad day in someone's laboratory. It was not a mistake. Almost the entire Greenland ice sheet has captured these dramatic variations.
It was a paradigm shift, really, for scientists' understanding of how fast the climate could change.
Right, so what does it have to do with the AMOC?
Well, they suspect that the AMOC had something to do with a lot of these swings.
Okay.
So if we look back at the last 20,000 years, there were these 2 dips in the air temperature in Greenland, and those line up with dips that they found in records from the bottom of the ocean 4,000 kilometers away. So this is the Bermuda Rise, which is a big bump on the seafloor near that deep current that moves North Atlantic waters south. And it collects sediment, about 10 centimeters after 1,000 years, which doesn't sound like a lot, but in a lot of other places, it's like 2 centimeters after 1,000 years. So for decades, paleoceanographers have been analyzing core samples from this site, and they're often looking for these guys.
Some kind of shelled creature.
These are tiny organisms called foraminifera, and they're amazing because they're made of a single cell and a shell. They're a cell and a shell.
They are beautiful little shells, and you can see their beauty under a microscope, but they're the size of a small sand grain.
Cool.
As these organisms were building their shells, they were capturing a picture of what the water was like then.
Many members of our group are hand-selecting individual specimens using ultrafine paintbrushes, ultrafine.
And the researchers found that there was an increase in nutrients in the water near the seafloor around the same time as those dips in temperature that we saw in the Greenland ice core. If you remember from our layer cake of water masses, the Antarctic bottom water, it has more nutrients than the North Atlantic deep water. So an increase in nutrients at the Bermuda Rise indicates that there was a bigger pool of water from the south there, which means that the overturning of the North Atlantic was shallower and weaker during those periods.
If the current that's taking cold Arctic water south gets weaker, that allows this southern water from Antarctica to make it further north and reach this Bermuda Rise. And so we already have seen that we think the breakdown of this current makes Greenland and that sort of area of the ocean cooler because there's less heat exchange. So it would make sense for the cooling of Greenland to happen at the same time as increased nutrients reaching the Bermuda Rise.
Yes. And they have several other indicators that point to a shift in the AMOC around those times, probably as a result of an influx in meltwater that would have lowered the salinity in the North Atlantic.
All of those things combine to tell us that the AMOC must have been, certainly was different, and it looks like it was weaker.
It seems like this overturning circulation has 2 or more different states that it can switch between. If it collapsed to a much weaker state, that transition would take about 100 years. So we would have some time to adjust, but we're talking about major shifts in weather and agriculture, on top of all the other changes that are going to come from greenhouse warming.
If this were to happen, we would see like a large-scale reorganization of the present-day climate, especially Northwestern Europe. There, the changes can be quite spectacular, and then not in a good sense. Seeing like large-scale cooling, less precipitation, higher sea levels.
The location of warmer sea surface temperatures shifts to the south, and this whole tropical rain belt shifts to the south. And basically that means that areas which used to get like this rain belt coming in, giving them a lot of rainfall, basically a monsoon, will not have that rain belt coming there anymore because it's moved to the south.
So what everyone wants to know is whether we are going to cause the circulation to switch again. And there's good news and bad news. The good news is we have a much better way of measuring it than we used to. If you were scuba diving around this latitude, you might spot a glass ball connected to a very slim cable. And if you follow it down, you'd find a big steel sphere and then dozens of instruments interspersed with more buoys, and finally, a big old weight holding it all down.
Oh, wow. It's a buoy that's anchored, but it's anchored 4,000 meters deep.
Yeah, and again, we have the Eiffel Tower here for reference.
Nice.
When you put these moorings out into the ocean, you tend to put the top out, and you will start, say, 5 kilometers away from where you actually want to deploy the mooring, and you will slowly move the ship along, and you will pay it out, the wire out, and bolt the instruments on, and slowly deploy it. And you basically get to the end, maybe a couple of tons of iron, which you then put over the side, and then you will release that iron anchor.
This is how we monitor the overturning circulation.
Okay.
And if you look at this diagram, you'll notice that the moorings are clustered on the western and eastern sides of this ocean basin.
Totally.
And that's because they're using the density differences between the two sides to calculate the flow between them, just like they used to do with the measurements from the ships.
Gotcha.
So this array got started in 2004, and as the data came in, it was really surprising.
For the first time, we actually had a measurement of the strength of this overturning circulation. We found that wasn't only just changes every hour, there were changes every day, the monthly changes, and then there were seasonal changes. And now we're starting to see actually decadal changes.
And you can see there's sort of, if you just squint your eyes, there is a gentle weakening
Yes.
across this entire time period.
They just don't know if it's still within the realm of normal variation for this system because all we have is 20 years. They have arrays now that are monitoring the overturning in the north and the south as well. But we're just kind of limited by how short all of these records are.
We have to really carry on observing at 26 North, probably around till 2035, even up to 2040. So we can definitely confirm that that signal is actually a weakening signal.
But I think for some experts like Stefan Rahmstorff, who joined us for our Science Paper Book Club earlier this year to talk about this, they think that we shouldn't wait to sound the alarms.
We can't predict for sure what's happening, but we have to warn about a substantial risk.
If we get to a point where it's definitive that it's going to happen, it feels like by that point, it will be very hard for us to do anything about it. Like if there's some definitive, oh yeah, it's definitely collapsing now. It's like, well, that would have been good to know 30 years ago or something like that.
Yeah, which brings us back to the cold blob. These surface temperature measurements, where the cold blob shows up, are a much longer record than the arrays that we were just talking about. And so a lot of scientists see that blob as sort of the key persistent signal that the overturning circulation is slowing down.
But like in the last few years, really, there's been a lot more evidence coming out that the magnitude of the cold blob that we see couldn't really happen without AMOC weakening.
It is not like a signal of an AMOC collapse, but mainly of an AMOC weakening. And the more weaker the AMOC gets, the larger this warming hole becomes.
The tool that we have to try to figure out what will happen is climate models, which simulate the Earth using math. And the bad news is that the models are giving a big range of results. What they agree on is that the circulation will weaken under global warming. Whether it will tip into a collapsed state depends on stabilizing or destabilizing feedbacks that the climate models are not totally capturing.
In most climate models, the AMOC is overly stable. So that means it takes like very large amounts of forcing, either freshwater or climate change, before your AMOC starts to collapse. And usually they are tuned in such a way that they have like a correct AMOC strength compared to observations. So the mean strength of the AMOC is very accurate in most climate models, but during the tuning process, the sensitivity is lost.
I think we take for granted that science can make sense of anything with enough observations and experimentation. And the researchers are kind of poking and stretching these models to try to come up with early warning signals of a collapse. But the truth is, we are not going to have a clear forecast on this.
I think it's one of those things that we're just at the edge of what we can even conceive in terms of like, you go to the beach, you look out at the ocean. It's the biggest thing you've ever seen. I mean, it's water as far as the eye can see, and you're seeing a tiny little fraction of it. So to imagine the swirling chaos that is going on and trying to model it seems, I mean, I'm amazed that we've gotten this far, that we've sort of teased out some of the little signals. But you can't capture all that complexity with our current technology.
I want to end our tour on this chart of temperatures from the Greenland ice core. Remember, this shows the past 100,000 years, which means that our species has been around for more than twice as long as this. But how long has farming been around? Or the idea of having a home in one place, in a village with lots of people, with predictable food supplies and medicine and technology and science and YouTube videos about science. These things emerged from stability, from this kind of unique stability that we have had during the Holocene. And that's not to say that we are going to go back to those wild swings from the last glacial period. The climate is a very different climate now than it was then, but we are making an experiment of a climate that has been very kind to us.
And there's a bit of an expression in the earth sciences that anything that has happened can happen.
It's not even the abruptness of tipping, it's the irreversibility, which I think is something that, policymakers or people need to consider. It's the fact that it's not just a little toy to play with, we could be changing things for generations to come.
Thank you so much for watching to the end of the video. I am genuinely so grateful for your attention to this story. I hope you can tell that we put a lot of time and thought into these videos, and there's not like a big company or budget behind this. It's just 3 of us trying to make this channel work, so we rely a lot on the support of our Patreon community. If you'd like to join up, it's patreon.com/howtown. Hope to see you there. Thank you so much.